Well, you know calculus. So what about our function Rn times m to r? And here are some examples. So for example, Rn to r basically is just distance function or norm. Mn to r is the matrix norm or general version like this. All these are, you can do whatever you want. But we only focus on finite dimensional vector space. First, the notation. We write something like this. This is called domain. This is called codomain. And then in one dimension case, you know this. Okay, I'm not going to talk about the details. Okay, you know all of them, I assume. Okay. Then the first thing is called directional derivative. We have a function f from x to r. What is this x? X can be anything here, but for simplicity, I just consider Rn. The directional derivative of f at x, so x is a particular point, with respect to the direction v is this limit. Some people use h, I always use t. So it's like this, your function value evaluated at a new point. That means x moves along the direction v minus the original value divided by t. This f is a scalar function. That means what? This f is output is r. We later will talk about what happens if output is a matrix or output is a vector. Okay, now the output of f is scalar. So the output is a scalar. xv are both vector in the set x. Okay, xv are in the domain. Okay, so domain is x. X is a subset of r. To make it very precise, x has to be an open set such that when we talk about derivative, it is okay. But we don't go too deep. Okay, you know the idea is that. Okay, done. Okay, then this is what? This is a limit on t. This is not a limit on x, and this is not a limit on v. So okay, this should be t. I make a mistake, so this should be divided by t. Okay, and then the notation are these. These are many notations. Different books use different notation. I always use this one. I strongly recommend don't use this one. This one is confusing, so better use the first three. Okay, I use the second one. So how is the directional derivative generalized? The first one. Okay, this is revision. So df dx is just what? It's just this thing. This one is for any dimension, right? Because this is for n dimension. So this one is just r1. So that means it's n1. Okay, and because we have n1, then what are these x and v? These x and v are in the domain of f. That's definition of a function, right? Then because domain now is r1, so xv becomes one-dimensional vector. One-dimensional vector means what? One-dimensional vector means it's a number. So what happens if it is in r2? So this is the illustration of r2. If we have r2, x1 are two-dimensional vectors, so we have something that written like this. So in other words, if we have one-dimensional vector, that means we have this thing. Because it's one-dimensional, it's forcing this v1, v2 to be the same number. But when we are having higher dimension, this v1, v2 are free. No need to be v1 same as v2. We can have any v1, any v2. So therefore, this makes the thing complicated. The idea is that, okay, in calculus, you know, usually we talk about a left-right limit. Okay, limit exists if the left limit equal to the right limit. And then in complex number, complex analysis, you know, we need to talk about limit exists from any direction. So this is the same idea. Basically, the idea is v1, v2 can be any number. So therefore, this generalizes the one-dimensional case to many dimensions. Then we now have many possible directions. And this actually makes everything complicated. And because of this kind of thing, this is reason why we need to talk about linear algebra, topology, why there's a ball. Because a ball means you have a point in all the direction you want to go. And this kind of thing is exactly for this. So that's why we talk about, if we go to the detail, again, I'm not going to the detail, everything is defined as what? Norm-ball. So what I mean is that, what is the df dx? Is the limit of x go to x0, something like that, right? Okay, I don't write down the whole thing, okay? These are all R, but if we have general case, first of all, this is vector, this is a vector, okay? Then, this thing have multiple directions we can move, so we need to use topology. But if this f output is also a vector, then we need to put a norm here. Then this generalizes to other thing. And this is the reason why we talk about topology, open ball, last time, and why we talk about linear algebra. Okay? So this is the idea. Go back to here. This is v. V is also input. So this thing actually have two things. One is x and one is v. So that's why we write this. And that's also why people write this bracket, two bracket, because we have two input. Alright? And then, because of that, v is also can change. So you can have this. So directional derivative alpha v plus beta u, you have this. These are, again, details. I'm not going to talk about how to prove these, why they are true. Okay, we are not talking about analysis, functional analysis. No, we just use them. And then you also have this product rule and chain rule. This will be useful later on when we talk about chain rule. And then what? Now, I just told you that this thing can go crazy. Then now let's talk about the crazy thing. So in infinite dimensional space, when n go infinity, then we have generalization. So this is what I just said, right? This is the classical one dimension, high school or year one. Then if n is larger than 1, you have general version called directional derivative. And then if we go to bigger dimension, we have Gateaux derivative. And then if we even more general, we use a norm instead of the function value, then we have Fréchet derivative. And this is the relationship. Here's the important thing. In finite dimension, that means n is just number, let's say 10-dimensional space, they are all the same. These are all the same. So Gateaux is this. Gateaux, what's the difference between Gateaux and directional derivative? Directional derivative is this. But now I put something here, so you can think of this part is the directional derivative, okay? And then what? And then now I put this part here. This part actually is the gradient, okay? But later we don't care about what's the gradient at the moment. So because now we don't know what's the gradient. But let's say that we have this. What is this? This is a linear function L like this, and we want this limit to be 0. What does it mean? It means this. What is this part? This part is the directional derivative. This means the directional derivative is what? I can move this part. Okay, of course, I need to put the denominator in the bottom, right? But if you look at it, this t and this t can cancel each other. Let's ignore the limit for a moment. Then they cancel each other. I can move this to the other part. So this thing approximately means what? This thing approximately means this df is approximately LV. Okay. So in other words, what does it mean? It means, what is this? df dx, but multi-dimensional version. It's saying my multi-dimensional version is approximately a linear algebra matrix multiply my vector. This not equal because I am not talking about the limit, but let's say we don't care about limit, okay? Then we have this, right? So basically, what's the idea? This is very general, right? What's very general? Well, in one-dimensional case, I write this as one-dimensional case. We know what, right? What is this? This is what you learn in high school, right? You say, oh, this line, this is a triangle. This thing divided by this thing, limit go to 0. Then you have this df dx. Now we have what? We have multi-dimensional version. So it's like we have a surface. Okay, we have a surface, and then we have a surface, and then it's very complicated to draw. But now I have a point here. Then I'm doing this thing. Now I have a plane, something like this. This plane is this, but it's 2D. Very difficult to draw, but you understand the idea, right? Then this is the plane. What is the plane? It's a linear subspace. What's linear subspace? Is a matrix. So that's why it's the same thing. So this is approximately this. Then of course this is approximately this. Then this is the first thing. If I put the linear map on top and I subtract it, then what? This is equal to 0. Then this is called Gateaux derivative. And then here's a funny thing. If I instead use a norm, put a norm here, and then here is not t, it's the whole thing, norm. Okay? This is Fréchet. This part is directional derivative, okay? This part is directional derivative. This part is also the linear map. This part is also the linear map. The difference is, first of all, this one equals 0. What is this 0? This is a vector 0. This 0 is not a number 0. But this 0 is a number 0 because this is norm, so it's a scalar. This is norm, it's scalar. So in other words, this is saying that if my directional derivative is approximately a linear map at a point, then this L thing is my gradient. And I want them to be equal in the limit sense. Limit means very, very, very small, right? So in the limit sense, that means when they touch each other, this approximation error gives me 0 error. And the 0 is in the sense of a vector. For Fréchet, it says that, this is a little bit more general, it says that I don't care what L you give me and what direction V you give me, as long as their difference measured in norm is 0, then this is a derivative. So this one is more general than this one. Because this one you are saying that I need vector equality. So this is saying like, what? This is saying like I have an A and I have a B, I want this to be 0. This is saying that I have an A, I have a B, I want this to be 0. This to be 0 means a whole vector subtract each other is 0. And then you know what? A vector multiply each other is a bunch of things, right? Then it is possible some combination of AIB, AIBI, AJ, BJ give you 0. That means this is actually broader than this one, so that's why we have this, okay? But in finite dimensional case, they are the same. Because in finite dimensional case, the vector representation is unique. Therefore, this one gives you this one. So therefore, in finite dimensional case, they are the same. Then you will ask, why do we need to know two different things for the same thing? Because it's useful. Useful for what? Useful for compute gradient. So here, fourth thing. Now I'm going to tell you the fourth one is, if we talk about the multi-dimensional vector calculus, we have 4 things. The first one is to compute this. This is the most stupid way, don't do this. The second one is to use directional derivative, which is do this. The third way is to do Gateaux derivative, which is write something like this, then this L is the gradient. The fourth way is to do Fréchet derivative, which is consider norm and write something like this, then the L is the gradient. So you actually have 4 ways to compute gradient. By using this, directional derivative, Gateaux, or Fréchet. And I will call all these 3 just directional derivative because they are all the same thing in finite dimension. So that's the idea. Okay, so now I just said I have 4 things, right? Now I'm going to talk about the last one, this one. Okay, the partial derivative, you write this. I have a f, Rn to R. The ith partial derivative, you write this. This is what? This actually defines as the directional derivative with the special direction that V is EI. So let's recall what's directional derivative. Directional derivative is this thing. This V is an input. That's why I write this way. Now, if my V is standard basis vector, that means EI in linear algebra. then this is called ith directional derivative. And I write this. So this is the mathematics. I write in a very big form, then you understand what I mean. So I have an x, value x1, x2, x3, x4 up to xn. And now I have what? I have, okay, I make a mistake, this should be t, but anyway. And then what? I add t, but now this is e what? Ei. So at the ith location, there is a one here, and all the rest are 0. And then I subtract my original value. So this is what I have, right? This is, I only change one small part in my function, and I take the limit. So this is direct partial derivative, okay? And again, you have many ways to write it down. Usually, people just write this one, okay? Nobody will write this, I believe. Okay, nobody write this. I do not recommend write this one. I also do not recommend writing this one, okay? So usually just this one, okay? And then gradient vector. What's gradient vector? Gradient vector is just these stacked together. And since these are directional derivative with a specific direction, so I can already write like this. So now this is different. Why? Partial derivative is what? Partial derivative, that means I write this is a what to what mapping. It's a Rn to R mapping. Why? Because my input is a particular x. Because I'm doing this thing as my whole operator. So this whole thing is a Rn to R. So it's a output is one dimension. What is this? Gradient vector is I stack all of them together. So gradient is what? I write this, okay? Some people want to make it absolutely clear, spell the whole word grad. Okay, that's also okay, okay? But I write this simple. Then this is now Rn to Rn because it is what? I have a vector input, x is a vector, and I do this process, I have another vector. So this is different from directional derivative. And because this E1, E2, E3, whatever thing are what? Orthogonal to each other, so I can also write in this form, right? So this is like what? Directional derivative on the first thing, and all the rest are 0, plus directional derivative on the second thing, and the rest are 0, and then so on, and then directional derivative on the last thing, and the rest are 0. And because this is because E1, E2 are like this, orthogonal to each other, okay? And the whole thing will be directional derivative with a lot of things in each boxes. This one comes from this one comes from second one, this one comes from the last one. This is due to linear algebra, orthogonality. And now, let's talk about the relationship between the directional derivative, direction and gradient in finite dimensional space. And then we have this first theorem. Again, we don't talk about the proof. What is this? This is directional derivative. So this is definition. So I'm going to write this, okay? So triangle means definition. This thing defined like this. This thing is what? It's a number. It's a scalar. What's a gradient? Gradient is a vector. So you cannot say scalar equal gradient because scalar is not vector. So now we have to make vector into a scalar by dot product. This is dot product. Yeah, I seldom write this. I do not want to write this because it will be very confusing. So I usually write bracket, okay? So dot product give you a scalar, and this scalar is exactly directional derivative. This is the usefulness. Why we talk about this? Because if you want to find a gradient, you start from here, you get something in this form, then you get this. That's the idea. These are details. And why this is true? Because of this. If we are in infinite dimension, sometimes we don't have inner product expression, then this does not work. But those are crazy things. We don't talk about crazy things. We talk about simple things. So we now have this, right? So I want to look into what is this. So first, this is the definition of directional derivative. dvfx is this. And then by definition of partial derivative, each of the xi partial derivative is just directional derivative with the ei. Now I'm going to go linear algebra. What is v? V is iv. What is I? I is a bunch of e. What is v? V is v1, v2, v3, v4. So I can say v is this, right? This is basically saying v is linear combination of standard bases. Okay? Then what? Now I have this thing I just told you. Gradient is also summation of these. So here's a funny thing. Gradient is also something, a linear combination of standard bases, right? So v is a combination of standard bases. Gradient is also combination of standard bases. So what is this thing? Right? This gradient, this part, is this part. So I have this part, which is this part. Okay? This is what I just told you. Now what about this part? It's a standard basis, linear combination. So I have this part. Okay? Now, because linear algebra, everything is linear, I can move this outside, right? So I move this outside. I have this. And then what? And then this summation is for all ij, but e is orthogonal to each other. So only ei is 1. Other thing goes away, right? So this is by linear algebra. So now I have this, so I have something like this. Well, this of course is this, right? Come on. And then what does it mean? It also means what? If I have fx plus tv, if I now do Taylor approximation on t, then it will be what? Right? So what is this thing? Which is this thing? It's exactly the first order Taylor approximation of this thing on t. Then everything makes sense. This is why you have this. Because what is this? This is exactly approximation of the slope if you don't take the limit. If you take the limit, you have the slope. So everything makes sense. So that's the idea. And of course, this is not proof. Why? Because if you need to prove, first you need to prove this limit exists, and then you need to prove this limit exists equal to this thing. Okay, many details. The epsilon delta thing, I'm not going to do that. So basically the idea is what? To prove a limit x go to something is you need to prove for all epsilon larger than 0, there exists a delta larger than 0 such that all the x in the neighborhood of your A implies the gap of your x minus b is smaller than this. These are the full proof, right? Now, if I want to do it here, I need to use topology and linear algebra version because the v can change from anything. Here it's not. Here is that neighborhood is in real number, it's just left and right. But now, if I have a point, neighborhood can mean a ball. That's why I need to talk about what? In the multidimensional version, if for all epsilon larger than 0, there exists a radius r such that x inside open ball near the A with radius r imply the distance between my x and the limit, which is b, smaller than epsilon, and this distance is measured by open ball. So these are the thing. So the proof structure is the same, but the details are more complicated, and then you need to talk about what's open ball, what's compact, what's closed, what's bound, what's no. Okay. The idea is you can prove this.